Bismillahirrahmanirrahim. Assalamu alaikum. I am Nazir Ahmad from the Oxford Education System. Today our second lecture of physics is from chapter number 10, and today our topic is the ball and bowl system. Bowl means pyala and ball is small ball of metal like iron and copper, etc. This is another example of simple harmonic motion. Today we will prove that the ball and bowl system is also example of a simple harmonic motion. First of all, this is the bowl and this is the ball. The ball is at rest and its weight mg is acting downward, and the reaction of the surface of the bowl is upward. This is r. These are opposite in direction and they are equal, so they cancel each other, and the net force on the ball in this position is 0. So we can say that ball is at equilibrium position, that is at rest position. Here no force is acting on the ball. If we apply a force on the ball on the right side and we move it on this position, the ball now is at position A. We apply a force F. Force is equal to mg, weight of the ball. Now we will release the ball from the position O. It will move downward due to the gravity. The gravity is the force that act on the ball toward the downward, and it will pull it toward its mean position. Now the ball will move toward the mean position. It will move speedily, and its acceleration is directed toward the mean position. And due to inertia, the ball will not come to rest at the mean position. It will move toward the point B, and it will now move slowly toward the B, and the ball will reach at the position B. In this case, the ball is moving slowly and its acceleration is negative, and a force is pulling it toward the mean position, and ball is moving upward slowly, and its acceleration is opposite to its motion, and its acceleration is always toward its mean position. In this way, the ball will rest for a while at B, and then it will again start to move toward the position O. Center position is called O. It is equilibrium position. For some time, the ball will move from A to O and O to B, and then B to O and O to A. In this way, there is a resistance of the surface of the ball, and it will retard the motion. It will slow down the motion of the ball. After some time, the ball will come at rest at the mean position. In this situation, we can say that the ball is moving from A to O and O to B. In this situation, the acceleration is always directed toward the point O. Either ball is moving toward B or towards A. We can say that its acceleration A is directly proportional to the displacement x, and its direction is always toward the mean position. At the mean position, its speed is maximum, and at B and A, its speed is lowest, that is 0. And we can say that its energy is maximum at the position O, and its energies are minimum at the position A and B. All these characteristics are matching with simple harmonic motion. So we can say that the ball and bowl system is also an example of the simple harmonic motion in which acceleration is always directly proportional to the displacement, and its direction is always toward the mean position O. Now we will discuss another example of simple harmonic motion, and this example is simple pendulum. The motion of simple pendulum. Simple pendulum is also an example of simple pendulum. Simple pendulum is also an example of simple harmonic motion. We will prove that how will it move, and its motion is also simple harmonic motion. First of all, we will try its example. This is a support. We can bind a thread with its force, and on other side of the thread there is a bob, bob. Bob is a small ball of metal. just like iron or copper, etc. In this position, the ball is at x and its weight W is equal to mg is moving downward and tension in the string T is moving upward. This is the simple pendulum. In this state, the ball is at S and it is in equilibrium position O, and there is no force acting on the ball and the force is equal to 0. Now if we move the ball toward the position O, this is position A, we can apply a force F on the ball, and if we release this ball, it will move toward the position O again. At this situation, there are many forces. Tension T in the string is vertically upward, and there is another force that is Fx, and it is along the string Fx, and this force is Fy. If we divide the components of force F into two components, one is Fx and other is Fy. Fx is along the string, and we can say that the tension and Fx both cancel each other and there is no motion along this line. Hence, the final and net force is Fy, and Fy is equal to F sin theta. F sin theta means F is equal to mg, it is equal to the weight mg sin theta. This is the force that is responsible for its motion, and this force will move the ball toward the position O. We can say that three forces are acting on the ball and two forces cancel each other, and net force is only Fy, that is equal to mg sin theta. This force is responsible for the motion of the ball toward the mean position. Now the ball will move. The ball will move toward the mean position O. The ball is moving towards O at high speed, and it will not stop at the position O due to the inertia, and it will move toward the position B, and B is another extreme position. Ball will come to rest at the B position for a while, and then it will move again toward the position O. In this situation, when the ball is moving toward O to B, it will move slow down and it will come to rest at B, and in this situation its acceleration is also directed toward the mean position because here acceleration is negative, and it will then move toward the B. It will move again speedily to O, and then it will not come to rest at O, and it will move towards A, and after some time it will continue its motion from A to B and B to A, or after some time due to the friction of air which is also present in the air, the ball will come to rest at the position O. In all these situations, we can say that acceleration A of the ball is directly proportional to the displacement x, which is a characteristic of simple harmonic motion, and the direction of acceleration is always from A to O towards the mean position, and when it will move from O to B, then acceleration is also toward the mean position O. In all the motion, we can say that acceleration is always directly proportional to x, and its direction is always toward the mean position. This is the characteristics of simple harmonic motion. We can say that the motion of simple pendulum is also a simple harmonic motion. At the end, the time period for the simple pendulum is 2 pi L over G radical sign. This is the formula for the calculation of the time period. Time period is a term, for example, time required for one vibration is called time period, and we can put the value of pi, length and G, and then we can calculate the time period T. Our length is start from this position and at the center of the ball. Here is the center of the ball. This is the length of thread, and half ball is equal to the length, and G is equal to 10 ms minus 2. This is gravitational acceleration, and the value of the pi is constant. Pi is equal to 3.14. In this way, we can calculate the time period of a simple pendulum, and it is an example of a simple harmonic motion. Here are some terms related to the simple pendulum. These are also the topic of this lesson, and first definition is about vibration. What is vibration of the simple pendulum? Vibration means one complete round. If we start from A, ball will start from A, it will move towards O and then B and then it will come back to O and A. Here we can say that there is completion of the one vibration from A to B and then back to A. This is one complete vibration. Other definition is time period. Time period is denoted by capital T, and this is the time required for one vibration. For example, we say that we will release the ball from A, it will move toward O and B and then back to A. It requires, for example, 2 seconds, and this is the time period for one vibration. Time period required for one vibration is called time period, or it may be 2 seconds, 3 seconds, 1 second, or half second. Third definition is frequency. Frequency is denoted by small f. Frequency is defined as number of vibrations completed in 1 second. एक सेकंड में जितनी वाइब्रेशन कंप्लीट होगी, that number is called frequency. For example, one vibration from A to then back A. In 1 second there are 3 vibrations. We can say that frequency is 3. If there are 5 vibrations in 1 second, then we can say that frequency is 5. Another term here is amplitude. Amplitude. Amplitude is denoted by A. A for amplitude, and it is the maximum displacement from mean position to the extreme position A. For example, simple pendulum, it is the mean position A and it is the extreme position A, and this distance is called amplitude A, or it is the maximum distance. The ball will move toward the A and it is the last position, that is maximum position from here to the mean position. This distance is called amplitude. Here there is a numerical example at the page number 6. We can now solve this example with the formula of time period T is equal to 2 pi L over G radical. And I will read the question and then we will write the data about this numerical example number 1.1. Find the time period and frequency. Time period is equal to question mark, frequency is equal to question mark. We will find both of these things. Of a simple pendulum, 1 meter length L is equal to 1 meter. At the location where G is equal to 10, value of G is equal to 10 ms minus 2. This is the data of the numerical, and we will apply this formula and putting the value of D. T is equal to 2, value of pi is 3.14, value of length is 1 meter, and value of G is 10. First of all, we will multiply. This is 6.28 and we will divide 1 by 10. This is 0.1. 6.28 multiply the radical of 0.1 is, we can calculate this with the help of the calculator, and the final answer is 1.99 seconds. Now we will find out its frequency f. Formula of f is 1 over t. Frequency and time period are the reciprocal of each other. F is equal to 1 over t and t is equal to 1 over f. Both these formula are related with each other, and f is reciprocal of t and t is the reciprocal of f. We will put value of t 1 over 1.99 and we will divide it by calculator, and the final answer is f is equal to 0.5 hertz. The unit of frequency is hertz and it is denoted by hz. It is the end of our topic. Thank you very much.